Our response to the amazing emotion is how to integrate the beautiful aesthetics of the furniture, like tables, and aesthetics of dynamic motions, like a machine constantly moving based on the data and energy.
Transform is about the simplicity of motion emerging from the complexity of the computational world.
So usually a furniture is a static object. but we wanted to give it some kind of motion, to give it some life form, so to explore the interplay of static and dynamic, which we can achieve with these pins that react to you, but also can display any content.
We don't want that the furniture will become to be more important than the motion itself, but we still want to make it feel like it's a one unified design and they're not separated.
The main thing is it's a very complex machinery. We have over 1,000 motors that we need to control precisely with a computer. So for us the biggest challenge was, instead of trying to hide the complex machine, we make it disappear through the beauty of motion.
We propose a new approach to physical telepresence, based on shared workspaces with the ability to capture and remotely render physical shapes. We explore physical telepresence through 3 different shape display systems: asymmetric teleoperation with shape capture and rendering, bidirectional interaction through shape capture and rendering, bidirectional interaction through deformation. Our teleoperation system enables capturing and rendering hand shapes for presence and manipulation. Our system is based on a depth camera connected to a remote shape display. Video of a shape display is shown on a horizontal screen, while a Kinect captures the user's hands. Remote experts can, for example, provide assistance and instruction to a local user in different contexts. They can also dexterously manipulate various physical objects. By altering the rendered shape, the remote operator's capabilities can be increased. To avoid obstacles in cluttered spaces, hands can be rendered without arms. Or shape output can be switched on and off to move around objects. Pointing on top of objects is also enabled by this feature. Users can rotate the scene, scale their representations. These transformations can, for example, enable users to handle larger objects. Physical shapes can be replicated and mirrored. By leaving a copy behind, the user can create static shape features. The hand shape can be replaced with different tools to manipulate objects more effectively. These tools include a claw to pick up objects, hooks for reaching, and ramps for sliding objects. Our second prototype enables bidirectional shape capture and output. It renders captured shapes remotely. Remote users can collaborate through connected objects for tangible interaction. Here, 2 tokens are linked and the remote user's hands are rendered physically. Alternatively, hands can be projected on the surface while the objects remain connected. Here, a remote object is rendered physically by the shape display, and a user can manipulate it through a separate gesture zone above the object. Alternatively, a brush tool allows the user to translate the remote object by pushing into the side of its local rendering. Our third prototype allows for collaboration through bidirectional deformation and output on shape displays. 2 shape displays can render the same connected 3D model, allowing both sides to modify the underlying geometry. In another application to convey remote presence, the shape displays render the inverse shape of each other. Pushing into a pin will raise its connected counterpart. An elastic mode conveys if someone on the other end is pushing at that very moment. This system can be combined with vertical screens for an enhanced sense of presence. We conducted a preliminary evaluation to get a more nuanced picture of remote object manipulation strategies and interaction techniques. Participants were asked to move a remote sphere to a target location by using a variety of different interaction techniques.